All right. To add on to what I said about part B earlier, so in the system, right, in the system, the mass of the block, the mass of the block of foam stays the same. So the large M will stay the same, and then the mass of the dart in part B right now, the mass of the dart will stay the same. Mu, mu constant, mu k will stay the same, and gravity will stay the same. And then in part A and B, force would stay the same, and force would stay the same. So if we look at this equation, then every other variable would stay the same. Every other variable would stay the same except for length. So length and distance would be, if there'd be a greater length, then the distance would be greater. So that is why a long tube will create a longer stopping distance in part B. Right. For for part C, give me a second. So part C, suppose students experiment with a fixed tube length L in a variety of darts while applied force F constant. Some darts have a high, excuse me, some darts have higher masses than others, but are the same aerodynamic shape. Assuming air resistance is negligible for the darts, should the students use a dart with a large mass or small mass to make the dart block stopping distance D the longest? Um, okay, um, so FT is equal to MV. But in this scenario, in part C, it says that the tube length L will be fixed, and the force will be constant. So Ft will both be constant. So then it leaves us with mass and velocity that can change. And then the mass and the velocity will determine the momentum, which will determine the stopping distance. And so MV, so the initial momentum would be MV plus mass of the dart plus velocity of the dart, initial plus mass of the dart times velocity of the dart, initial plus mass of the block times velocity of the block initial, but the initial velocity of the block is 0. So that you can cross that out, which will equal to when the dart and the block hit each other, their masses will combine, and then this will be m plus m plus velocity final. They will both share the same velocity. Okay, so mass and velocity have an inverse relationship with each other. So when mass goes up, velocity will go down, and vice versa. So in this, we see that when the mass goes up, velocity goes down. And
Did you
then,
see Kevin Gates' Instagram story?
so if the so if we look at the final, it's mass plus mass equal to final velocity. In this mass system, there are two masses, the mass of the block and the mass of the dart. But um, if we increase the mass of the dart compared to the mass of the block, the mass of the dart it'll have less effect on the entire system. So what's most important in this final in the final for the once the dart hits the block is the velocity. So the larger the velocity, even though the mass, so we know that mass and velocity have an inverse relationship. So the larger the velocity, the smaller the mass. But the mass of the dart compared to the mass of the block is at its the mass of the dart is less than the mass of the block, so it have less an effect. So even if the mass is lower, if the velocity is high, the velocity will have the velocity will affect the final momentum more. So the higher the velocity, the higher the momentum be. And since they have an inverse relationship, a smaller mass will cause a higher velocity, and a higher velocity will lead to a higher momentum, and which is what will change, which will affect the stopping distance. So a small mass will lead to the longest stopping distance. And to recap, the mass and the velocity have an inverse relationship. When the mass goes down, the velocity goes up, and when mass goes up, velocity goes down. And when we look at once the dart hits the block, and we look at the final momentum equation, it's mass plus mass times velocity. Um, so the mass of the dart and the block, they become one system, and the mass of the dart compared to the mass of the block it is uh, it is smaller than the mass of the block. So the mass of the dart has less of effect has to the overall mass of the system. But for the velocity, well, if we look at the final then, or the final momentum velocity equation, then velocity will have a greater effect on the final momentum of the system. And so a smaller mass will lead to a larger velocity, and that smaller mass will affect the system less. So, and the larger velocity will help create more momentum. Therefore, the small mass will have the largest stopping distance d. All right. So part D, calculate the speed of the dart immediately after it leaves the tube. Okay, so it gives us um all the numbers. Okay, the speed of the dart immediately after it leaves the tube. So I will use common form. So VF squared minus VI squared is equal to 2 delta x. All right. So okay, so VI squared, since the dart at at the start the dart does not move, so initial is 0. So just cross this out, and then we bring final velocity to one side, so it's 2a delta x. V squared is equal to 2a delta x. All right, so a, we can use a by using the by using F is equal to m times a. You can find a using the force equation. All right. Okay, so we're given force. We're given the force of the we're given the force, so it's 20 equal to the mass, and the mass of the dart is 20 grams also, but 20 grams equals out to 0.02 kilograms. All right, and then is 0.02, and acceleration is what we're trying to find, which is the 5.02, then A will equal 1,000. So, and then for delta x, so it asks calculate the speed immediately after it leaves the tube. So the only distance it travels is just the length of the tube. And the length of the tube we're given is 0.05 meters. Therefore, the final, once we plug everything in, Vf squared is equal to 2, acceleration of 1,000 meters per second. That 1,000 delta x 0.05. And then all we need to do is plug it into our equation. Plug into our, okay, we get Vf squared is equal to 1,000. Just square root that. Wait, let me write it a little bit neater for you, Luong. We just square root both sides. We're left with V is equal to 31.62 meters per second. Oh, I forgot. The acceleration is meters per second squared. There we go. Right, velocity is 31.62. Part D. So let me get that. There we go. All right, part E. Calculate the speed of the dart block system immediately after the collision. Okay. So the speed after. So we're gonna be using momentum. So it will be mv initial. So mass of the dart, velocity of the dart initial, plus mass of the block, capital M, versus velocity of the block initial. And since it sticks together, then we know it's inelastic, and for inelastic, we combine the masses. So M plus capital M is equal, and they share the same velocity at the end. So VF final. All right. So we know that the block isn't moving, so immediately we can cross this out. And then we're given the mass of the dart, 0.02 kilograms, 20 grams or 0.02 kilograms. And then velocity, we just calculate the velocity once the initial velocity, which is right here, 31.62. So parentheses 31.62 is equal to. So it says that the capital M, the block, the mass of the block is equal to 30 grams, and 30 grams is just 30 grams is equal to 0.03 kilograms. So mass of the dart 0.02 kilograms, mass of the block 0.03, and it's equal to 0.505 kilograms. 0.05 kilograms. I got it from adding the two masses together because when they collide at the final, they stick together, so they're together. And then VF is what we're trying to find. And then all I need to do is divide 0.05 over to the other side. I just do the algebra, 0.02 times 31.62 divided by 0.05 is equal to VF. So put it in your calculator, and VF will equal 12.6 meters per second. All right, part F. Derive an expression for the acceleration A of the dart block system as it travels across distance D in terms of the given variables. So what are we deriving? We're deriving acceleration of dart block system. Okay. So we want A and N. So we can start off with F times A, force, or M, right? Or more specifically, net force. Mass equals mass of acceleration. But so once it hits the dart block system, so in the dart block system, once the dart hits the block, the only force that's acting on it would be friction. Since there would be no other force because after the dart hits, there's no other force that acts on the block. So net force is really only Fk, since Fk is the only force acting on it. Fk is equal to M A. Okay, so what is Fk? We know that Fk is just we know that Fk is really just, or we know that mu is equal to Fk over Fn. So we just multiply Fn to the other side. So Fk is really just mu times Fk is really just mu times Fn. And then so once again mu times Fn. Mu is a constant, but Fn is really just Fg, because if we look at the system right now, scenario, there's only one force acting downward on the block, and the only force acting downward on the block is gravity. There's no other extra force that's acting downward on the block. Therefore, Fn will equal Fg. And what is Fg? Fg, and then we can expand that out even more, because Fg is really just m times gravity. But in this, and for the mass of the system, mass of the dart block system, it's just the dart and the block added together. So it's just m plus capital M times g. And then we just need to add it all back in together. So mass, and we just need to put it back right back into each other. So Fg is equal to Fn, and mu times Fn is equal to Fk. Therefore, if we put it back into this, force equation, then Fk is equal to Fn. Fk is equal to mu times Fn, so mu times Fn, and Fn is really just m lowercase m plus capital M gravity is equal to the mass. But again, mass of the dart block system is just the mass of the dart, lowercase m plus mass of the block, capital M, parentheses around that, times A. And then now, if we look at both sides, we can just cancel out m plus capital M, or we can divide both sides by m plus capital M. So they cancel each other out because they just divide. We just divide one side against the other, and we are left with mu g is equal to a, acceleration. And this is the formula we derived for acceleration of the dart block system. Right, part E. Block that up. Alright, so part G. Using conservation of energy, calculate the speed of the dart block system the instant it leaves the table. So conservation of energy. So it's energy at the beginning, mechanical energy initial is equal to mechanical energy final. Okay, so energy stays the same from initial to final. But if we look at the system right now, it's only moving in a horizontal direction. Um, so there's no potential energy, since potential energy is mgh, it has height. But since it's only in horizontal, it's only kinetic energy. So it's um, 1/2. So at the final, the energy at the end, we can just replace that. It's just kinetic energy. Therefore, we just have 1/2 mv squared final. But then at the initial, what we're looking at is it will also be 1/2 mv squared, but there is there you go, 1/2 mv squared. But there's also another force acting on it. There's another force, which is friction, which we discussed about in the previous part. And the force of friction will cause energy, will cause us to lose energy, which is the energy of friction. I have that right there. So since they asked us calculate the speed of the dart block, we can use this using conservation energy. We can use this formula. And the final kinetic energy is 1/2 mv and 1/2 mv final squared, and then the initial is 1/2 mvi minus the energy lost due to friction. Okay, so now we just start plugging things in. So first, what is energy due to friction? Energy lost, energy due to friction. We can really just replace that with vi squared minus energy of friction, which is just the work of friction. F of k. There we go. Is equal to 1/2 squared, and what is so energy friction is really just the work of friction, and then we can expand that more out, which gives us the work of friction, which is what? It's just force of friction times the displacement is equal to what we established earlier. MV final. Okay, and now we just have to start plugging things in. Okay. Oh, we have to figure out the force of friction. And from the previous part, we know that force of friction is equal to mu is equal to mu is equal. Oh shoot. Equal to mu um mu m plus capital M. Right. So we know that mu is mu is 0.14. Oh shoot, right there. Increase the size. 0.14 and mass. I mean lowercase m. Mass of the dart. 0.02 kilograms plus mass of the block is 0.03 equal to F. Okay, therefore Fk is equal to give me a second. Which is equal to 0.0686. Alright. And then now that we have everything we need, all we need is plug it in. So 1/2 m, which we know m, the mass of the system, m which is asking the mass of the system is just mass of the dart plus mass of the block. So the dart block system. So we just add the mass together. We know that from previously it's just 0.05. Initial velocity, we figured that out in a previous part 2, which is just 31.62 squared minus, and then now for the friction, Fk, just figured out was 0.0686 Oh shoot, let me zoom out more. Point 0.0686. Here, parentheses that times 0.0686 times that change in x, and we know that the change in x is just the distance that the dart block mass traveled before it fell, and it's given to us as d, variable d, which is 0.05 meters. So 0.05 parentheses that is equal to 1/2 mv squared. Alright, oh, I forgot. The m, again, we said the mass is really just the dart block system mass, which is just really you add the mass of the dart plus mass of the block, which is 0.0. Okay, I messed that up. 0.05. Please ignore the bad handwriting. 0.05. There we go. The final, which is what we're trying to find, squared. And then, now it's just basic algebra. So let me put it into a calculator. First here. So 1/2 times 0.05 is 0.025. Right? 1/2 times 0.05 is 0.025. So here we'll divide 0.025 across this entire thing, 0.025. Or here, let me make this easier a little bit. Okay, I take back dividing by 0.025. Let me erase this. Okay, alright, there we go. Okay, okay, take that back. I don't divide. Okay, so we see both sides of the equation. 1/2. Wait, okay, scratch everything except with that algebra part again. Yeah, you're just gonna algebra it out. So first, let's start with the left side here. Well, let me start all that algebra again. So 1/2 times 0.05 is 0.25. 0.25, and 31.62 squared is 999.824. So 0.025 times 999.824, which is minus 0.0686 times 0.05. 0.686 times 0.05 equal 0.0343. Give me a second. 343 is equal to 1/2 times 0.05 is 0.025 v f squared. So 999 times 0.025 is equal to 24.99995 24.99561. So 24 minus 0.0343, which we get as 24.9613. 9613 is equal to 0.025 bf squared. Divide by the 0.025. You get 998.4524 equals to VF squared, square root both sides. Then we end up with a final velocity of 31.5982 meters per second. Final velocity of 31.5982, which is a very small decrease from the velocity found earlier, which is 31.60. Okay, so to recap, we use conservation of energy, mechanical energy, initial is equal to mechanical energy final, which is, but we figured out that it's really just kinetic energy. So kinetic energy at the beginning minus that equals the final kinetic energy. But at the beginning, or at the initial, it's 1/2 mv squared minus the energy lost due to friction. And then once we found out the energy lost due to friction was really only just 0.0343, very minimal amount of lost energy due. So we did 24.9 99561 minus 0.0343 is equal to 24.961 as the kinetic energy at the initial. Then we use algebra again to find the velocity at the final as 31.5982, which is a very small decrease. All right. Now we'll open a new page. This is messy now. All right. Part H. How far horizontally X will the dart block system travel before striking the ground? All right. So part H. How far horizontally? Oh, I reset the question. Okay. So this will be projectile motion. Yeah, projectile motion. So we're trying to find how far horizontally it strikes. So trying to find change in x. But the change in x we know the equation of change in x is vi initial, but initial in the x direction. Vi x, the initial velocity in the x direction times t. Okay, and okay, so the block just moves, just falls off the thing, off the uh, off the place. So we know that there is no y direction. There's no angle that the block shoots up from. The block only travels straight, therefore it's only moving the x direction. Therefore there's no launch angle. So we can just, the initial velocity, we can just keep as 31.62 since there's no launch angle. It just launches at 0 degrees. It launches flat, so we don't have to do anything special to it. So 31.62 time is equal to change in x. And so for time, we can use displacement formula. We can find the how far it falls, and we can use that to find um, the time. Okay, so the height of when we look at the scenario, the height of how far the block is from the ground, the height of it is we're given as 10 meters. So right away, delta y is 10. And then uh, displacement formula is just 1/2 at squared plus vi. But remember, we're in we're looking at the delta y, the vertical. So vi in the y direction this time, t. All right. So and then so now we can just plug everything in. Or here, I forgot to say that the VIY, since as we discussed earlier, there's no launch angle. It doesn't launch up or it doesn't launch down. It just goes flat across, moves horizontally. Therefore, there is no VIY. There is no initial velocity in the y direction. It's just 0. So we can just cross this part out right here. So we're left with 1/2 at squared. I forgot the squared right here. Um, the excuse me, acceleration in the y direction we just know is just gravity, which is just negative 9.8, and then we're left with t, which is what we're trying to find. And then now it's just simple algebra again. 1/2 of 0.98 is 4.9, I mean negative 4.9 t squared is equal to 10 divided by negative 4.9. We divide both sides by negative 4.9. Excuse me. Um, we are left with 2.04. Oh, I forgot to include. Okay, so since we're moving downwards, we're moving down, so we're moving in the negative direction. We're moving down, so the change in y, I mean the distance change in y is negative. I forgot to mention that. So since we're moving down, the 10 previously is actually just negative 10 since we're moving downwards. So the change in y is negative. So negative. So we get 2.04 is equal to t squared. Square root both sides. We are left with t. Time is equal to 1.43 seconds. Then now we just plug it back into the equation we have on top. So change in x is equal to 31.62 times 1.43. And now we are left with change in um, give me a second. Okay, I have just realized I made a gigantic mistake. Okay, so going back, part E, this is so in part F, let me write it out again. Um, I made a gigantic mistake in part. I made him. Oh shit. Okay, I'm tripping up. Okay, I just realized I made a gigantic mistake in part G. Okay, so in part E, I was using. Wait, let me write it out. Okay, 1/2 mv squared minus the work of friction, which is Fk times delta x is equal to F is equal to kinetic energy at the end is KE. But I realized that I was using the velocity of the dart, not the velocity of the dart block system for part G. So let me just do all the algebra over again. Mass of the mass, which is 0.05. Yeah, so I was using the velocity of the dart instead of using the velocity of the dart block system for part G. So let me redo everything. So velocity of the dart block system 12.6 squared minus the friction, which is 636. And then, so this is equal this is equal to 3.9669 minus is equal to minus 0.0318 is equal to 3.9658 3.96582 is to 1/2 mv squared, which is really just which again 1/2 times 0.05 is 0.025 v squared that we're trying to find. So we divide both sides by 0.025. Then 150.6328, 158.6328 square root. Then up here v is equal to 6345. I mean, not 64. It's equal to 12.594. This is the velocity. This is the velocity for part G after it leaves the table. And then going back to the previous part. Open. Shoot. For part H. Give me a second. Let me find it. Okay, so then here. Okay, so this is not 31.62. It's 12.594 times 1.43. Sorry about that. Box that out. Is equal to 18.010 is equal to the distance it travels.